Okay, so yeah, got two cameras going, the usual one and the Zoom version. Hopefully you can see this okay. So you're gonna have two different views here. As I mentioned, this one I'm gonna post on YouTube, which is the normal regular camera. This one I will send you guys a link to do that. So it's currently recording the Zoom version as well, so we should be good. A couple questions to get out of the way since I was being asked. I already told my other section this, but testing and quizzes are suspended, so we're not having a test this week. So I got a couple of people emailing me about that. I believe I mentioned it in the last video, but I don't know. Maybe some people just didn't hear. So yeah, testing and quizzes are completely suspended at the moment. And yeah, in terms of what exams would look like when we do start giving them again, I do not know. We are going to do pretty much whatever the math department says we're going to do. So that is going to be what we're going to do. And at this point, I don't know what that is yet. So hold on, I'm just trying to get this more centered here just a little bit. Yeah, so exams and quizzes are suspended. Definitely what I will be doing starting this week, what I would do is I would post mock quizzes and mock exams, which you're going to be grading yourself for the time being, just for you to know where you stand with this whole thing. But as far as official testing and quizzes go, that would count towards their grade, that's kind of up in the air right now. We're still deciding on what to do. Yes, if we do have an exam, I will let you guys know at least a week before I give it how is it going to be administered first of all, how it's going to count towards your grade, all that good stuff. Yeah. Something else some people were worried about, which I guess I'll just address right up front. And I just want to kind of address it, jump into this, and what I'll do is I'll hold a mini Q&A session at the end where I can answer all these questions that are coming in. But the important things that you should know at the moment, quizzes and tests are suspended. Nothing official will be given by way of quizzes and tests for the near future. The math department is going to figure out a way that we can do that fairly, and as well as just maintain the integrity of the exam at the same time. And when they do, they're going to pretty much tell everyone what we're doing, and at that point I will let you guys know. I will let you know at least a week before I give a test how it's going to be administered and pretty much just the specifics. In the meantime, I'll be posting mock quizzes and mock exams, I suppose starting this week, so I guess maybe like Wednesday or so I'll post something. We are going to have classes using Zoom, because I tried the Blackboard Collaboration Ultra thing and it doesn't like me. Blackboard has never liked me, that's why I don't use it. So what I will do is I will have Zoom running while I'm recording on the regular camera. So I'll be recording in two places. I'll post what I'm recording on my regular camera on YouTube. Whatever is being recorded on Zoom, I will send you guys the link for it. So only my class will have the link to the Zoom stuff, including the chat and all that good stuff. So yeah, that's pretty much it. Another thing that some people might be worried about at this point is just overall grades, like how is your grade going to be calculated, how is this going to affect your standing in the class, this whole thing. If you're not really doing quizzes anymore, you're not really doing tests at the moment, like how is this going to affect you? So let me just say as a blanket statement, like in general, as far as I'm concerned, everyone is still in the running for an A. So wherever you are, in theory, you can come back from this. So, and I don't expect that to change. Whenever I do figure out a way to actually test you guys correctly, I'm going to make it as fair as possible. I'm going to give you the best chance as possible. and I really just look, and this would be in general, even without this situation that we're currently going. I really look for improvement over time. So even if we had a test and you messed up on it, or you've been messing up on quizzes or whatever, what I'm really looking for is that over time you guys improved. And if, by the end of the semester you can show me, oh, I really understand what's going on, I'm not going to count the past, what's behind us, as heavily as usual. So that's just something I just wanted to throw out there. So everyone in theory is still in the running. They're still pretty good. So the only thing is, for some of you it might be very difficult. Like if you have a really low grade, it's going to be hard for you to actually improve to the point where you can actually get a good grade. But as far as that is concerned, I'm not going to stand in your way as far as that is concerned. So that's what you should be aware of. So don't worry about anything like that. Whatever happens, whatever happens from now on, just know that the grade you'll get in this class will be pretty much the grade you would have gotten if none of this ever happened. So still keep putting your best foot forward, still trying as hard as possible, still try to study and improve on what you've been lacking, and everything should be fine. Yeah, so don't worry too much about the past. I'm reading some more questions here. Like I said, keep focusing. Don't worry too much about the past. Just kind of try to improve. As I mentioned to my last class, so that my philosophy on teaching is, now in some sense, academia is not the same as real life, and I'm fully aware of that. But for the most part, I like it when academia tries to prepare you for real life. So when it comes down to that, what you'll notice about life is that there are times when, yeah, you mess up and, there's really no way you can get a do-over really. So I know a lot of professors would like, if they find that the whole class messes up on a test, they give them a makeup test or whatever. Like, I'm not into that stuff, because I don't think that gives you a fair expectation for life and how to actually come back from a failure or just things not going your way. Sometimes you try to prepare, sometimes you slacked off and it doesn't work out and you get hit with it, and that's just a part of your past now. However, life usually, as long as you're alive, there is hope. Life usually gives you a chance to kind of learn from your mistakes and make up for that in the future. So, you go to the Olympics, you don't get a medal, they don't just allow you to do your event over again on the spot. No, in 4 years' time you come back and hopefully you can do better. So there is this hope in the future. And so that's what I kind of try to make my classes like. Yeah, you might have messed up on a bunch of quizzes, you might have messed up on a homework, and I'm not going to allow you to redo those. But in the future, as long as you can show me, you know what, Jhevon, I learned from my mistakes, I really messed up here, now I'm better. If you can show me on a final that you now understand all the material that you messed up with on test 1 and on the quiz, then I kind of don't really care about test 1 and the quizzes at that point. Because at that point, if you learned enough to say earn an A, I'm not going to be like, yeah, well, 2 months ago you were a D student. Like, I don't think it's fair for me to judge people that way. So I really take improvement into account and just, judging you as fairly as possible in the moment that I'm actually putting down the grade. So that's kind of how we will deal with things now. It's kind of how I always dealt with things, but I do understand the fact that we're at a distance. It might give you some more anxiety because you don't know, but just so you know, don't have that anxiety. I'm not here to actually hold anyone back. I want the best for you guys. I want you guys to learn as much as possible. I want you guys to have the best grade as possible. I do want you guys to just be all around awesome and not have to worry about these things. And I'm not really going to hold the past over you that much. As long as we can move forward and have the future be great, everything will be great. That being said, some of you do have hard work ahead of you, and that's just how it is. But as long as you put in the work, you start to try to improve. It's probably going to be a little bit harder now because you probably can't, if some of you might need tutoring and things like that, you can't really get that in person, and I don't know. So it's probably going to be a little bit more challenging to improve and get the help you need, but whatever you have to do, do it. And if you do make the improvement, I will be there to have your grade reflect that. So I think you, yeah, don't worry about that stuff so far. I didn't see any homework for today. I don't know. I'll check the homework right after right after this lecture, and make sure everything is up to date. Currently, you should have had homework up to 10.6, I want to say, and I might also make the 10.7 homework live, based on what we're going to do today. But it's already been a while, so what I want to do is let's just get through this lecture. Hopefully the view is not bad. The view from the main camera is going to be better. That's going to be posted on YouTube as normal. I want to get through all the things I planned for today's lecture, and at the end I'll stick around for a small Q&A session. If anyone still has any more general questions, I can deal with them then. So at this moment, if you have a question, I think if you type it here, it'll give me a ping, or you can just unmute and ask a question if you want to do that. Yes, you will have the opportunity to ask questions mid-lecture. And that's the whole point of me even doing this Zoom thing in the first place. So, yeah, so you stop me whenever I say something that you don't understand or want some clarifications on, and this is good. I actually have a better turnout now than I did the last time I did this, so that's great. Yeah, let's actually just jump into it. So we are going to continue. Hopefully you can read this somewhat. Like I said, there's a better quality video coming up. And yeah, so let's get started. So last time we left off with an example of an alternating series, and we were trying to approximate the series with a partial sum. And this kind of led us into the idea of estimating series. So just a few main points here I just wanted to remind you guys of. Finding out what a series converges to in general is very difficult. It's not something that's easy. Most of the tools that we have for doing that are beyond Calculus 2 level. So yeah, it's hard to do in general. But what we can do is a lot of times we can approximate a series using some partial sums. So instead of me adding up an infinite number of terms and then coming up with an answer, something that the series converges to, what I would do is I would add up a finite number of terms. Add up the first 100 terms, the first 1,000 terms, the first 1,000,000 terms, or whatever, right? If I add up a finite number of terms, the first few terms, the idea is sometimes you can use that as an approximation for the series. And the reason is, we know that for a series to converge, the AN must be approaching 0. It won't always converge if it approaches 0, but that is a necessary, not sufficient requirement. Which means, eventually, the things you're adding in the series are going to be so small that there comes a point where you can kind of start to ignore them. So the idea is, we want to approximate the series by ignoring a lot of the terms. And we can do that by just adding the first few terms, the first few partial sums. Now, you might be wondering, if I'm ignoring some of the terms, how close am I getting to the actual answer? That might be a concern. And so this is where we have series estimation theorems coming in. And we are going to talk about 3 of them today. So they tell us how good some particular partial sum is to the actual answer of the series. So here we have some series, let's say it adds up to S. If I were to write it out, it looks like this: A1 plus A2 plus A3 plus A4, going on forever. The first n terms, remember when we added that up together, we got what was called Sn, which is the nth partial sum. This is just the sum of the first n terms. Then you have the rest of these guys going off, all the terms going off to infinity. Now, I didn't mention this terminology in the last lecture, so I'm going to introduce the terminology now. The part that comes after Sn, the part that comes after the sum of the first n terms, this is called the remainder term, right? So we have the nth partial sum, we have the nth remainder term. So the nth partial sum is the sum of the first n terms. All the rest, the entire tail that's remaining, that's called the remainder term. So basically what you can think of that guy is, that's the guy that is the error in our approximation. The difference between the actual sum and the sum of the first n terms can be measured by the magnitude of this remainder term. So that ends up just being the error in our partial sums approximation of the series. And the idea is the following. If we can make this error small enough, then for all practical purposes, the nth partial sum can be accepted as the sum of the terms in a lot of cases. So when it comes to like purists and math people, we often want to know what exactly is S. When it comes to like engineering and applications and any scientists using this in the real world, where series come into play a lot, or if you're looking at Wolfram alpha when you're calculating a series and it gives you an answer to some amount of decimal places, what it actually does is it uses a partial sum to approximate the series that you're looking at. And the idea is, what it does is it takes enough terms so that the error is acceptable. There is some acceptable tolerance. So you can say, oh, I want to be correct to the first 5 decimal places. All they need to make sure is that the magnitude of the remainder term is less than 0.00001, right? And so that's kind of the idea that we're going with now. I'm going to show you in 3 scenarios how to actually approximate series using a partial sum, how to know how many terms you would need in order to get it to your answer within a certain tolerance, how to make your error as small as possible, just some theorems about this error. And the last time, I did tell you about one of them, that was with the alternating series test. So let me just remind you of that. So last time I mentioned, and I'm going to rewrite the alternating series test in terms of this Rn business. So last time I mentioned the alternating series approximation theory. So this is the theorem that says, suppose you have an alternating series, say -1 to the n converges, right? So you have an alternating series, you know it converges by something like the alternating series test, which tells you about conditional convergence or whatever. Then it turns out, if you have a convergent alternating series, then the magnitude of Rn, which is the same as the actual sum of the series minus the sum of the first n terms, it turns out you'll always have an upper bound for that. It is actually going to be less than or equal to the an plus first term. So we saw that last time and that was pretty nice. I had a ding here. Is there a question? Oh, someone just said cool. Never mind. This was how we could bound the remainder term for the alternating series. Pretty much if you add up the first n terms, how far are you away from the actual answer? Well, the magnitude of the n plus first term actually tells you that, which is, it's pretty cool, it's pretty nice, and I believe we also did an example. So the example was the alternating harmonic series. So last time, we were given -1 to the n over n, and we saw this converges. then what we did was we found S5. S5 was the sum of the first 5 terms. This was -1 plus a half, right? I think we did S4. Minus a third plus a fourth. That was something like -7/12. And then we asked the question is, how good an approximation is S4? And the answer was, well, the A fifth term, the next term, right? So when this says A n plus 1, A sub n plus 1, that's just talking about the n plus first term. A5 was actually 1/5. And that was, of course, 20%. And so the answer was S4 equals -7/12 is within 0.2 of the sum -1 to the n over n. So whatever this actually adds up to, we don't know. It turns out that if I add up the first 4 terms, I would get -7/12. That's actually 0.2 away from what the actual answer is, right? So if I add up the first 4 terms, the 5th term is going to tell me how close I am to the actual answer. If I add up the first 100 terms, the 101st term is going to tell me how close I am to the actual answer. If I add up 1,000,000 terms, the 1,000,001st term is going to tell me how close I am to the actual answer. So this happens with the alternating series test. The sum of the first n terms can be approximated. How good an approximation that is given to you by the n plus first term. And I left you guys off with a question, so this is still a little bit of recap. But I left you guys off with a question. If I had that series and I wanted to make sure that my error was within a certain tolerance, everything, is that a question? No, I think that's just people joining. Okay, so no questions yet. So now I left you guys off with a question last time. How many terms are needed to approximate this guy, -1 to the n over n, with an accuracy of 0.01. Okay? So let's say you only care about the answer to 2 decimal places. You want it to be accurate up to 2 decimal places. How many terms would you need to add to actually achieve that? So it turns out we can use the alternating series approximation theorem. And any idea on how we could actually get that done? Anyone has any suggestions? Besides Joel, because I think Joel was in a previous lecture. He's getting doubly educated. How many terms would I need to make sure that my error term is less than 0.01? So I see some guesses. I see 10 terms, 99, 100 terms. Like, what's your reasoning? How did you go about calculating that? How did you get it? Okay, so that's funny. So David said this and someone like pointed up, like, yeah, what he said. Okay. So with an accuracy, usually you can think of this as the error is less than or equal to. If you took it as less than, that's fine as well. But we know that Rn, the error is going to be less than or equal to this guy, which we know is less than or equal to the an plus first term. Now all you can need to do is is just make sure that this guy is less than or equal to the tolerance that you want. So this is what you want. If that's true, then your remainder term is going to have less than that, which means the an plus first term is 1 over n plus 1, because my an is 1 over n. This guy I can think of as minus 1 to the n of 1 over n. So this guy here is my an. And so my an plus 1 is just going to be 1 over n plus 1. I just want to make sure that that is less than or equal to 0.01. Or, in fact, that is 1 over 100. And so, this means that I need n plus 1 to be greater than or equal to, well, 100 if I flip both sides. And so this means I need my n to be greater than or equal to 99. So if I am at 99, I can expect an error of this. If I want an error of less than that, I would just make this completely less than and just start at 100. So I need 99 terms. So that's the answer. We need 99 terms. If you want to be strictly less than this, you would say we need at least 100 terms. Depends on how I actually phrase the question. But yeah, so if I take minus 1 plus a half minus a third plus dot dot dot, going all the way up to like minus 1 over 99, this is going to be approximately equal to the entire answer to within 0.01. So if I only care about 2 decimal places, pretty much I would just only calculate the first 100 terms, which, yes, it's a lot, but 1, it's a lot less than adding up an infinite number of terms, and 2, a computer can do that no sweat, right? So the thing is, if you were to throw this into, say, something like Wolfram Alpha and ask it to tell you what that is, pretty much what Wolfram Alpha would do is it would add up enough terms to return whatever number of decimal places it wants to give you. So if Wolfram Alpha returned an answer that has 3 decimal places, what it actually did was it added up the first 999 terms, and then it just outputted that decimal answer as an approximation to your series. So for an alternating series, this is something that you can use to actually approximate the series. And it's pretty cool. It's pretty nice how that works out for an alternating series. The sum of the first n term is approximated by just the next guy, which is pretty nice. So whatever tolerance you want, just make sure that the n plus first term is less than that guy, and solve for n. That will tell you how many terms you need at minimum. So that's pretty cool. Yeah. Okay, so some people are like, it makes sense. All right, good. Yeah, that's pretty much it. So this problem, if it does come up, it would come up as another part of a question, right? So it'll be like part B of some problem. So it's not supposed to be totally difficult, but it'll be like something, if I ask you to calculate something with a series earlier on, then I might ask you as a follow-up, hey, how good is your answer? How would you approximate the answer to be within this tolerance? That might be something that I would follow up with. And I'll show you some more examples of that. Some more examples like that will actually come up in the next lecture, where we actually start to apply series to integration. It's going to be fun stuff. And we're going to approximate integrals using series. But that's it for the alternating series test. So it's a very important theorem, the alternating series approximation theorem. It's definitely one you should know. If I test you on an approximation theorem for a series, chances are it's going to be this one. So make sure you know the alternating series approximation theorem. if you look on past finals, so the past finals that are up for 212, the past finals that have been up for the old Math 203, you'll see pretty much every time they ask you to approximate a series, it's going to be an alternating series and they expect you to use this theorem. So it's a very common thing to ask about, and chances are I'm going to ask you about this as well. Here are a couple more that I'd like you guys to know. We actually also have a theorem for the integral test. So the integral test approximation theorem. Okay, so this says, suppose we use the integral test to show some series converges. Then it turns out that the following inequality is going to be true. The remainder term is actually going to be less than or equal to this guy from n up to infinity of f of x dx. Where f of x is the guy that which is equal to an when I just think of it as a continuous function. So remember, for the integral series, if you saw that this guy was positive, decreasing, and is continuous on the interval from whatever the starting point is to infinity, if I just thought of that as a function, just replace all the n's with x's and do the improper integral, that integral can tell me whether the original series converges or not. And so we're doing the same integral, except we started from the nth position. And it turns out that that is going to be an upper bound for your remainder term. The integral theorem, the integral test is also nice in that it also gives us a lower bound for the remainder theorem. It's going to actually be above n plus 1 to infinity of f of x dx. And this is where f of x equals a sub x. So that's pretty nice. And some people often wonder, they often forget, should the n be here or the n plus 1 be here? Which position do these guys show up in? And if you kind of look at it from a pictorial point of view, so let's say that's your f of x. Notice that your n would show up before the n plus 1. And so the area under here is going to actually be smaller than the area under here. Right? So you're actually getting a larger area by integrating from n onwards. This is actually going to be a bigger number than this guy, right? Because he starts later, and so the area, this integral here is going to give you a smaller answer than that integral there. So this is the way that the inequality should be turning. But, hello, did someone say something? Okay, so I think someone's talking. You should probably mute if you have to talk to someone else. Okay, so this is how we can actually do an approximation with the integral test. Your remainder term is actually going to be bounded by this. Let's do an example here. So I'm going to look at an example that we've actually done before with the integral test. Example. We saw that this series of e to the 1 over n squared the integral test. How good an approximation is, let's say, the first 5 terms? So that is the question. I don't know. Whose mic is it?
Sorry.
Okay. All right, cool. All right. So we actually did this guy already via the integral test. We know that that guy converges. In fact, it converges absolutely because that always returns positive values. If I were to just add up the first 5 terms of that, how good is that? Right? So, I mean, S5 here would just be, well, E plus E to the 1/2 over 2 squared plus E to the 1/3 over 3 squared plus E to the 1/4 over 4 squared plus E to the 1/5 over 5 squared. So I add up those 5 terms. How close to the answer am I? Anyone want to chime in and tell me what you would do here? It's probably going to be hard for you to actually type the answer up. Maybe just undo your mic. Someone brave, speak up. Okay, I hear you, Syed. Figure out something after. In the meantime, to make sure. Any ideas? Anyone? Nope. No idea what to do. Okay, but maybe I can make it a little bit easier. What if I were to ask you, can you tell me an upper bound for the error? Like, what's the worst case scenario? Like, how far could this possibly be off?
The integral of the lowest term.
Specifically, what integral you're talking about?
Fifth term. The integral of the 5th term. So the integral of a of n from 5 to infinity would be the upper bound.
Right, so S5 is going to be less than, well, the difference between S and S5 is going to be less than or equal to the integral from 5 to infinity of pretty much the an if you think of it as a continuous function, which is e to the 1 over x squared. Right, that's going to be the worst case scenario. That's as far off as will possibly be from the answer. And so that's just an improper integral, which you guys all know how to do. So you integrate that, you would get minus e to the 1 over x between 5 and infinity. And yes, technically you're supposed to set big N here, let limit as big N goes to infinity, but yeah. So the idea is, of course, if you plug in infinity over here, you get e to the 0 plus, plug in 5, you get e to the 1/5. And so that is actually going to be an upper bound for our error. That's the worst case scenario. This, by the way, is 0.2214. So by adding up the first 5 terms, we are off by 0.2214 at worst from what the actual answer is to this guy, right? So it's the answer is going to be within this, which is again kind of nice. You actually just integrate from the point at which you want to add up the partial sum, and that actually gives you an upper bound for your error. If I wanted a lower bound for the error, I would just actually integrate between this, by the way. This would actually be greater than or equal to from 6 to infinity of e to the 1 over x squared. So if I ask you for a lower bound on the error, you could actually just integrate from 6 onwards. If I ask you from an upper bound for the error, you will be within from 5 onwards. That's the most. So, I mean, you could also do this. This would be very similar. This would look like minus 1 plus e to the 1 over 6, which is roughly e raised to the 1 over 6 minus 1. So this guy is roughly 0.1814. So our error is at least this and at most that. So we're somewhere, we have a leeway of created by this window, which is, yeah, so which is kind of nice. So someone asked, we use the last term. I'm not sure what you mean by last term. In the question I specifically mentioned S5 here. So you can tell me that the error is at most this guy, which is that, and at minimum it's this guy. But if I were to ask you in a question like this, I would be more specific whether I want you to calculate an upper bound or a lower bound, right? So we can't be worse off than this, but we can't be better than that, is the short answer there.
Jhevon,
Yes?
what I by the last term was like for S5, for the upper bound, like for upper bound use like the last. That's why I don't understand like the upper bound stuff.
Well, the theorem, like how we might talk about this, is the theorem had Rn. So this is the error, the possibility of how far off you are from the answer. It's less than this, and it's greater than this. And this guy you might refer to as an upper bound for the error. Right? Because that's the maximum amount that the error could actually be. Whereas this guy you refer to as a lower bound for the error. So that's the minimum error that you could actually have. Like you're not going to be better than this error, but you're going to be less than that error.
So when using the S5, in as like the approximation for S5, you just like use the fifth term of the.
Exactly. So with S5, you would think of this as here, R5. What is the remainder after you added up the first 5 terms, which means your n is 5. You plug in 5 everywhere. Which is why we integrated from 5 onwards.
Oh, okay, thank you.
Okay?
Yep, thank you.
All right. Yeah. So that's with the integral test. One other one I want to do, and then we'll actually move on to some pretty interesting stuff, I think. It's kind of setting up for the next thing, which I think is kind of exciting. It turns out that the comparison test actually behaves very similar to the integral test, And you might remember that the comparison test that we did for series was actually analogous to the comparison theorem that we had for improper integrals. So the integral test is very closely linked to the p-series test and the comparison tests, because we kind of use the same kind of intuition to actually prove them. Even though I didn't prove them, in the background that was the same kind of intuition that we used. So with the comparison test, it's actually a very similar thing. We don't have a lower bound estimate for the comparison test, but we do have the upper bound estimate, and it's actually the same one as the integral test, believe it or not. So the third guy for the comparison theorem approximation. Now, in general, this is going to be kind of hard to apply, because you can use the comparison theorem even in cases where the integral isn't very nice. Especially with p-series. So if I ask you about this, I'm going to ask you about a situation where you would actually compare it to a p-series. So suppose we determined the series of AN converges by comparing to a series Bn, where Bn is a p-series. Okay, what am I saying here? That is, my AN was less than or equal to Bn, and Bn converged. Right, so suppose we're in this situation. This could work, what I'm about to say could work in general, but it's nice with the p-series situation because it's going to be an integral that we know about. Then, if Tn is the remainder term for the Bn series, then turns out our Rn will be less than or equal to the remainder term of this guy, right? Because this guy is larger than that, his remainder term is actually going to be bigger than that guy's remainder term. And this guy is going to be less than or equal to that, where this guy here, your f of x in this case is going to be your b sub x. So, example. So, which series do we look at? We can look at n plus 1 over n cubed plus n plus 1. So you could look over something like that. So let's make it this. I'm not going to do it, but we can show via the comparison theorem that this converges. You can show via comparison with 1 over n squared. Start from 1, just going to do this. That this converges. I'm not going to go through the details because we're past comparison tests now. So what you could actually do is if someone asks you, how good an approximation is what is the max error in using, say, S10 to approximate the sum. Right. So you could ask a question like that, and so you see something like that. It's not an alternating series test. It's also not something that you would use the comparison theorem, you would use the integral test on directly. But what you would have done to figure this guy out is actually use the comparison with this guy to determine that. And it turns out that you can actually use the integral test on this guy. And so you can kind of bypass, you can go straight through to the integral test approximation theorem and apply it here. And so if you want to know how good an approximation is the sum of the first 10 terms to this guy, what you can do is you can know that the remainder term, R10, is going to be less than or equal to the integral from 10 to infinity of 1 over x squared. Right, and that's going to be minus 1 over x, infinity, and 10. So that's going to be 1/10. So if you add up the first n terms, you will be within 0.1 of the actual answer for this particular series. So that's that one. So those are the three that I would expect you to know. For sure you need to know the alternating series approximation theorem, because that one they love asking you about. A departmental final asking you about this kind of stuff will more than likely ask you about that. And starting with the next lecture, we're going to see a situation where that kind of problem would come up. Yeah, the denominator here is n cubed plus n plus 1. So the integral on the P series guy that you use in the comparison is actually going to give you an upper bound for the error. That's pretty cool. Okay, so what I want to do now is, so we've been covering for our past few classes comparison tests for series. Series is just the sum of the terms of a sequence, and we just want to know whether or not these guys would add up to something meaningful if we're adding up an infinite number of terms. The comparison tests are what told us about that. We did like 10 of them. And now what we want to be able to do is, knowing that we used a particular test, how do we know how to approximate the series that we used it on to within a certain amount of tolerance? And that's what these kinds of theorems are about. So each test that I told you about has a theorem that goes with it, but I only care about you knowing these first three. The other ones can actually get pretty complicated to actually apply. So like the estimation theorem for like the ratio test, for example, is totally complicated. It's not something that I'd expect you to do as a part of a problem. But I can ask you about an alternating series approximation. I can ask you about a comparison test approximation. I can ask you about an integral test approximation. And those guys should be easy enough, computationally speaking, for you to pull it off in an exam. So those are the three you should know. Yes, T sub n is the remainder term for the Bn. Series. So now we're going to do something pretty cool. We're going to go into another topic. We are going to talk about power series, which is pretty awesome. So it's an application of series towards, I don't even want to say it's mostly used in calculus, but it's one of the most important applications of series for calculus, even though you would use them in other spheres as well. But when it comes to like why we really like talking about series, and how it actually helps us in doing computations in calculus, power series is kind of where it's at. This is section 10.7. So, I want to tell you what a power series is, some peculiarities about it, and we're going to figure out where they work. Next time I'm going to show you how we can develop power series on our own and how we can actually get them to be useful, how we can represent certain kinds of functions as power series and how they can actually help us do calculus computations. But for now, this is an abstract idea that I'm going to introduce to you guys, and we're actually going to put it to use starting in the next lecture. So let me actually give you the definition here. A power series is a series of the form so normally we started from 0 to infinity, and it looks like Cn x minus x naught to the n. So here we're throwing in a variable here. So this guy, we call it the power series centered at x naught. Right? So a power series can have what we call a center, right? And that's just going to be the value that's plugged in here. Now, x is a variable. Here, the Cn is a constant given by the output of a sequence. And x is a real variable. Our x naught is a particular real number. Right, so x naught is a constant. Your Cn is also a constant, however, it's given by the terms of a sequence. So what you'll realize is that we can actually write this out. So I'll give you some time to copy that. Maybe like take a screenshot. Give you a countdown, pause, 3, 2, 1, pause the screen, take a screenshot, do whatever. This will be on video anyway, but I want to continue writing here. So what this guy actually looks like if you start writing it out. Is he starts looking like you plug in n equals 0. You just treat this as you would a regular series. You plug in n equals 0, you would get C0. If you plug in n equals 1, you would get C1 x minus x naught to the 1. If you plug in n equals 2, so this is the power series centered at x naught. Plug in n equals 2, you get C2 x minus x naught squared plus C3 x minus x naught cubed plus C4, dot. So you start to look like that. Now, where its name comes from, so this is called a power series centered at x naught. Now, to make this a little bit more suggestive, you can probably see kind of the kind of thing that we're kind of aiming for here already. But to be a little bit more suggestive, suppose x naught equals 0, then we have if I were to go here and plug in x naught equals 0, this will look like x to the n. And if I start writing that out, you'll notice that this is c0 plus c1x plus c2x squared plus c3x cubed plus c4x4 plus dot dot dot. And now you can start to notice what, now that should make it obvious what kind of creature we're looking at here. It's a polynomial. In fact, it's a polynomial of what degree is this polynomial? Infinite degree, right? So here we took the object of a polynomial, which we know is a very nice object because they're continuous, they're easy to differentiate, they're easy to integrate. But now we start to look at them as like an infinite series almost. So we're kind of mingling the idea of a series with that of a polynomial, right? Now, since a function f of x equals x to the n is called a power function. That's the general class of functions. We get the name power series. So if you might wonder why, where the name power series came from, it just came from the fact that we're summing a bunch of power functions. Right? And pretty much what a power series is, it's like an infinite polynomial. It's a polynomial of infinite degree. And you might wonder, does it even make sense to define a polynomial of infinite degree? Well, we're going to talk about that pretty much right now. How do I know that something like this expression could possibly make any sense, at least in the way that a polynomial would make sense? So I'll give you some time to pause, take a screenshot, 3, 2, 1, pause, and then let's talk about what it would mean for such a thing to be meaningful. So power series, just a way to write down an infinite polynomial. Now normally when we talk about series having meaning, we talk about convergence. So let me tell you about the convergence of power series here. There is a theorem that tells us about the convergence. For the power series Cn x minus x naught to the n, there are 3 possibilities for its convergence. Just trying to get it in one line. Convergence. Here's one thing that could happen. The series will converge only at the point that you're centered at, meaning, so if I have a series, I have this power series, boom, Cn x minus x naught to the n, right? So this is C0 plus C1 x minus x naught plus C2 x minus x naught squared plus dot dot dot, right? Now, on its own, that's just some object to you. But if you think of it as a function where I can just plug in an x value, right? Once I plug in an x value, this here now just becomes an infinite series. It's just me adding up a bunch of numbers. when would that series converge when I plug in a particular x value? Well, one possibility is it will converge only if you plug in x equals x naught, meaning you're going to plug in a value that's going to cause this to go off to 0, that's going to go off to 0, blah, 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 and then this guy will just add up to C0, which is just some constant. It's just going to be one term in a sequence. That's going to make sense. So one possibility is if you plug in x equals x naught specifically, it will converge, right? So that's one possibility. Another possibility, and more namely, it's going to converge to the number c naught. It's going to converge to the first term of your sequence. Another possibility is that the series converges for all x. So you have this guy. Now it's just a huge infinite polynomial looking thing. Right? Which, how do you even know if that makes sense? Well, you plug in an x value. One possibility is if you plug in x equals x naught, it wipes out all of these guys, it'll converge to that guy. It'll just be the sum of that term. Another possibility is it doesn't matter what you plug in for x. I can plug in x equals 1,000,000, x equals 1,000,000,000, x equals 52, x equals pi. And this series is going to actually add up to something meaningful. That's one possibility. It will converge all the time on the entire real line. And another possibility is the third possibility is the following. It's going to converge on some interval. Namely, for all x values less than or equal to r, r is just a number called the radius of convergence. We're going to talk about that in a little bit. But it will converge for all x within this distance from the center, right? And that's it. That's all three possibilities. One thing I want you to notice is a power series is always going to converge. You'll never actually end up in a position where your power series diverges. It actually doesn't make sense to say that, which is kind of amazing. It's always going to make sense. The question is, where is it going to make sense? Is it going to make sense at this one point? Or is it going to make sense no matter what x value you plug in? Or is it going to make sense on a certain interval? And let's talk a little bit more about that, because the possibility 3 is especially might cause some concern or might cause some confusion. And if you don't get the notes here, again, I'll post the video and you can pause the video and actually copy it down. So let's talk about some illustrations of these guys. So in case 1, what do I mean? Well, if I imagine that this is the entire real line, like that's just a real number line, there is a point on the number line, which I would call x0, and we know the series only converges here. Meaning, at any other point I am on the number line, the series doesn't make sense. It will diverge, but it will converge at this one point. So here, what this basically means is that your R equals 0. This is your radius of convergence is 0. So that's one possibility. So this ROC is my short for radius of convergence. Okay. In the second case, what does that mean? Well, here's your number line, and there's a particular point called x0. However, the series will converge no matter what x value I plug in. So the series converges on the entire real line. Meaning, no matter what x value I plug in, it's going to make sense. I will get a list of numbers that adds up to something meaningful, and I can use one of the series tests to actually prove that this is the case, right? On the third possibility, so here, you would say that your radius of convergence is infinity. ROC is infinity. The third situation that I mentioned is you have the real number line of all possible x values you can plug in. There is an x value here called x0. But there is a window. There is a window of length r. So here's the point x0 plus r, and it goes back x0 minus r. And for everything in here, for all x values that I plug in this window, if I pick any x in this window and plug into the series, it's actually going to add up to something meaningful. If I pick any x value outside of this window and I plug into the series, it's going to add up to something that diverges. It's not going to work. So here is where your radius of convergence is r. Some finite real number. Of course, there's going to be some positive real number because it's measuring a distance. One thing you will notice here is that this naturally leads to something that's called the interval of convergence. So there's something called an interval of convergence. And that we might abbreviate with IOC. So in the first situation, the interval of convergence is, well, there is no interval of convergence. Namely, it converges for a single point. The IOC for the second case is the entire line, minus infinity to infinity. And the IOC in this case, IOC, that's going to be from x0 minus r all the way up to x0 plus r. And there is one caveat here. It may or may not converge at the endpoints. You'll have to check those separately. I'm actually going to do an example where we actually check all this stuff. Okay. So a power series, it's just a way to write down an infinite polynomial, a polynomial of infinite degree. Now, that polynomial, you just think of it as some function that you can plug in x values into. So you might want to know, what is the domain of this function? Where does the function work? Where does it actually make sense as a function? Well, there are three possibilities for that. It turns out it will always make sense as a function. It will always make sense no matter what. the question is, where is it going to make sense? How is it going to make sense? One possibility, it will make sense at a single point, at the point on the real line where x equals x naught. Everywhere else, every other x value you plug into the power series, it doesn't work. It adds up to something that diverges. Or you could have a series where no matter what x value you plug in, it's going to work no matter where on the real line you are. You plug in x equals whatever, it's actually going to add up to something meaningful. Then you have a situation where it only adds up to something meaningful within a certain window. And it may happen so the possibilities for the IOC, it may not converge at either endpoint, so x naught minus r, x naught plus r, or it might converge at the left endpoint but not the right one. It might not converge at the left endpoint but converge at the right one. Or it can converge at the endpoints and everywhere on the interval. So this is something that you'll have to check, and I'm going to show you how to check, right? So everything that I just mentioned, that's kind of just something to know. I'm going to actually tell you about how to actually figure out which situation you're in, where it would work, and maybe give you a little bit more intuition on how to actually determine what this will mean or how it's going to add up to something meaningful. But in the meantime, like take a picture of this and copy it in your notes. And this isn't even really necessary. Here I just want to give you some sort of intuition of what I mean by it only converges at one point versus on the entire real line versus in some interval. X minus x naught is less than r. And this actually comes from the fact that, of course, to just go by the algebra, x minus x naught less than r, we know that that means minus r is less than x minus x naught. Can unfold the absolute values like that, and then I can add x naught to both sides. So then I get x naught minus r less than x naught plus r. Right, so that's where this interval actually came from. So we have these possibilities. And whether it converges at the endpoints is something that you'd have to figure out on a case-by-case basis. Okay. So now, how do we go about actually determining these numbers? So those are the new concepts. What could I possibly ask you to calculate or do? What would you need to know how to do? You do need to know how to find the radius of convergence and the interval of convergence. How do we find the radius of convergence? Now, there's a nice calculus 2 answer to this. So if I ask you, find the radius of convergence or the interval of convergence of this series, of this power series, what are you going to do? You're going to use the ratio test. You will always use the ratio test. How do you figure out what is the radius of convergence or interval of convergence of a series? Use the ratio test. Use the ratio test, use the ratio test. You will always use the ratio test. It's always going to be the ratio test, right? Now there are other classes in which the root test might come in handy or whatever, but in the calculus 2 setting, it's always going to be the ratio test. You will always use the ratio test to determine these. What is the nice thing about the ratio test? Well, the ratio test actually gives you converges means this, which means ultimately you're going to end up with something less than 1. You're going to have some blah less than 1. And that automatically gets you an interval, right? You're going to have an interval automatically unfolded. Once you check something converges by the ratio test, you're going to get an interval anyway, just naturally, just by how the ratio test is actually set up. So you're always going to use the ratio test. The root test is a very common test to be used as well, but not in Calc 2. In Calc 2, if we ask you a question like this, the ratio test is pretty much what you're going to do, like all the time. So yeah, that's the answer. Use the ratio test. How do you use the ratio test? Let's do some specific examples. So we're going to do these. I will run through the first one for you guys. Then I'm going to have someone actually. Scary? It's not scary. Hold on. We're gonna. Oh, did you mean me doing this was scary, or just? Okay. Yeah. All right. But I do want you to just know, whenever you see this question, what is the radius of convergence? Use the ratio test. Let me scare the people on YouTube. Use the ratio test. Okay. Examples. Find the ROC and IOC of we're going to do those examples, and that'll be enough for us to actually get through and kind of understand the situation. So I'm going to run through the first one just to give you an idea, and I'll probably ask some people that help me out with the next two, right? Now, the first thing I want you to notice here is that these are actually power series. So first of all, this guy, notice that I can think of it as n equals 0 to infinity of 1 times x minus 0 to the n. So this is like a power series in which my Cn is always outputting 1 and my x naught is 0. Right, so that's a power series. This here I can think of as a series. Right, this is, I'm not going to tell you, I just want you to understand that these things I wrote down are power series. One way you can know it's a power series is just the fact that there's an x there as well as an n. This here, it's like I have 1 over 2n times x minus 4 to the n. So this means your Cn equals 1 over 2n. If your n is larger than or equal to 1, of course your C0 is just 0, because I started from 1, not 0. And here your x naught is 4, right? So this is a power series centered at 4. This is a power series centered at 0. This one is also a power series centered at 0. This is 1 over n factorial times x to the n. N goes from 0 to infinity. So this is a power series where my Cn is given by 1 over n factorial, and my x naught is given by 0. So I want you guys to understand that these are power series. These things that I wrote down, they are power series. If I actually wrote them out, they will actually start to look like polynomials. And when I'm dealing with each of them, I'll actually write it out so you can actually see, get used to what this object looks like. But in the meantime, copy these guys down and or take a picture, and let's actually jump into it. So the goal is to find the radius of convergence and the interval of convergence of these guys. So n goes from 0 to infinity of x to the n. Now, of course, if you were to start writing this out, plug in n equals 0, you would get 1, plus n equals 1, you get x, then x squared, then x cubed, then x4, plus dot, dot, dot. So it's just like an infinite polynomial where the coefficients are always 1, right? Now, the question is, what x values can I plug in that is going to make this guy work? Now, if I were to plug in, and so this isn't me doing the problem, I just want you to build a little bit more intuition of what we mean by convergence or what we're talking about. So, notice that if I were to plug in x equals 1, what's this guy going to look like? Well, it's just going to be 1 plus 1 plus 1 plus going on forever. Now, clearly, that diverges, right? Another possibility is I can actually plug in the center point, plug in x equals 0. What would that look like? Well, 1 plus 0 plus 0 plus da da da. Whenever you plug in the center point, the first term stays, but everyone else dies. This guy actually converges specifically to 1. Now, of course, we could actually plug in, say, something else, like x equals a half. So if I go to this polynomial and I plug in x equals a half, what's going to happen? Well, I would have 1 plus a half, plus a fourth, plus an eighth, plus a 16th, plus da da da. Now that should look familiar to you. That was actually the guy that I was using as an example with the dichotomy paradox. We actually know that this converges to, this will actually converge to 2, right? Because with the dichotomy paradox, we showed that this guy actually converges to 1. That's a way that you can walk a mile by slicing up the mile into an infinite number of halves. Then I added 1 more. So this will actually add up to 2, right? Now clearly what you can see from this situation is that this is a series that is in the third case. It's not going to converge for all real numbers because clearly I just plugged in a number and it didn't work. But it works at the center point. It also works at within a half a distance from the center point. But how can I find out all the possible x values where if I plug them into this polynomial, it will actually make sense, right? So when we want to find where the radius of or interval of convergence is, that's what we're figuring out. What are the x values I'm allowed to plug into this thing and it will make sense as a mathematical object? So, how do we do that? How would I find what is the radius of convergence or interval of convergence of this guy? Yeah, very smart. Yes, that's the one I like. Right? Not ratio test, like you're not sure. Ratio test, and you should even throw in a few exclamation points on that one. Huh. It's always going to be the ratio test. So, how do I go about finding what x values are going to work here if I plug these in? You're going to use the ratio test. So, that's what you're going to do. You employ the ratio test. Now, the ratio test will always be employed. I know a lot of people are, hopefully none of you have lost your job because of this whole thing. It's really sad. A lot of people are actually not working now. But the ratio test will always have a job. Hopefully you guys will bounce back. Yeah, it's going to be rough for a while. It's going to be rough, but we'll survive. We'll survive. The ratio test, still hard at work. It's always going to be around. So what would we actually do for the ratio test? What we would do is we would set up the limit as n approaches infinity of this guy to the n plus 1 over that guy. Right? That's the ratio test. You take the series, you plug in n plus 1, boom, you divide it by plugging in the nth term. So that's what we're going to have. Now, this simplifies, of course, so the x to the n is going to cancel that. You're only going to have just an x left here. Now, how did the ratio test show convergence? Pretty much, it only converges absolutely, by the way, whenever this limit, but by the way, what is this limit? So if the limit as n approaches infinity of this, well, there are no n's there, so it's just that. So basically, for convergence, we need the absolute value of x to be less than 1. Right? Because that's how the ratio test works, by ratio test. So that gives you, boom, radius of convergence automatically. That is 1, right? Because that is x minus x naught in absolute values is less than this real number. It's 1. So now, how do we go about finding the interval of convergence? Well, if x is less than 1 in absolute value, this means that my x is between minus 1 and plus 1, which means now what I would do is I would check endpoints. So I'm going to check what happens at minus 1 and what happens at plus 1. What? So now you go, if x equals minus 1, you go back to the original series. That would look like minus 1 to the n. So that is just 1 minus 1 plus 1 minus 1, whatever. But you can know that the test for divergence shows this diverges. So yes, you're going to have to know all your series tests, you're going to have to remember that. So yes, we're applying the ratio test, but when it comes to checking the endpoints, you're just going back to good old, all those series tests that we know before. Because minus 1 to the n does not converge to 0. So we know it diverges. Similarly, if I try x equals 1, I get the series of 1 to the n, and since a n would approach 1 in this limit, the series diverges. And of course, that means the interval of convergence is all x values between plus or minus 1. The radius of convergence is 1. So basically on the number line, this is a series that is centered at 0. It will go all the way down to minus 1, not including minus 1. All the way up to positive 1, not including positive 1. It will work in this window here. Notice that the radius, if I were to imagine that this was the center of a circle, right? The radius is length 1. So this here is r equals 1. There are a couple ways you could find the radius of convergence. You could find it from by just seeing that whatever your x minus x naught is less than is that. Or what you could do is you could actually just complete the problem, find the interval of convergence, find the length of the interval. It's also going to be b minus a over n, b minus a over 2. A couple ways you can get to that. So for this series, x to the n goes from 0 to infinity. It has an interval of convergence of the open interval minus 1 to 1. It has a radius of convergence of 1. Meaning, any x value I plug in this range will give me a summation that makes sense. Any x value I plug in outside of that range, like for example, I showed when we plugged in x equals 1, it didn't work. It's not going to make sense. Okay? So yeah, for this guy, interval of convergence is this, the radius of convergence is that. Let's do the other one. Pause or take a screenshot or whatever. Now we're running short on time, so let's actually do this together. Now what this guy looks like, you can start writing it out. Plug in n equals 1, get x minus 4 over 2, plus n equals 2, you get x minus 4 squared over 4. Plug in n equals 3, you get x minus 4 cubed over 6, plus x minus 4 to the 4th over 8, plus dot dot dot. So you get that infinite polynomial. Now, what is the radius and interval of convergence? What is what are the x values that I can plug into this and get something meaningful? How do I go about finding those? Ratio test. Always the ratio test. So. By the ratio test, what are we going to do? We're going to compute the limit, and it's always, of course, as n approaches infinity, of this guy to the n plus 1 over 2 times n plus 1 times the reciprocal of that guy, 2n over x minus 4 to the n. This is the limit. I'm going to start simplifying here. So this cancels that. The 2's cancel. And pretty much what I have here is I have n over n plus 1 times x minus 4 in absolute values. Okay, what is that limit? Well, x minus 4 in absolute values, right? Don't forget the absolute values, they're actually important. So now you're going to set x minus 4 less than 1. So right away that tells you radius of convergence is 1. Because that's the center point. This reminds you of x minus x naught in absolute values is less than r. Here your r is 1. 4 is the center point. Right? I'll show you another way to get the radius of convergence later, but you can actually get it at this point. Right? So that's your radius of convergence. Now you want to start finding the interval of convergence. Yes?
How do you know the radius of convergence is 1? Sorry.
Oh, because of this. So the radius of convergence is defined by this interval. If you have x minus the center point in absolute values is less than something, that thing is automatically the radius of convergence. So here, I had my x naught is 4. So this looks like x minus x naught in absolute values is less than this number.
How did I get the reason why it's more than sorry.
Huh?
I still did not get the reason why it would be 1 but not the other value.
It'll be 1 but not? Come again?
Why is it not like why is it 1 but not any other value?
Here's one way you can see it if the notation is confusing you. If you were to talk about this guy and rewrite it, this would be minus 1 is less than x minus 4 less than 1, right? So now if I were to add 4 to both sides, this would mean my x is between 3 and 5. Now if you were to write that as an interval, so the center is 4, it goes down as much as 3, and it goes as high as 5. This distance from the center to the outer edge is what? Well, it's 1. Right, so this has length 1. So the radius is, the interval that you're looking at is all x's between 3 and 5. Right? So if you look at half that length, b minus a over 2, you would get 1 as the answer. So that's another way to see it. So if determining it this early is a little bit confusing for you, that's fine. Just go to the interval of convergence, unfold the thing, and then measure it after you fix x in the middle. Right? So this tells you it goes between 3 and 5, half the distance between 3 and 5. So that's another way to look at it. ROC is equal to half the distance between 3 and 5. It's half that length. So it's going to be 5 minus 3 over 2, which is 1. So you'll get the radius of convergence that way. So you could even save that for the end.
So it will be true for all cases, right?
Yeah. Once you find the interval of convergence, the radius of convergence is half the length of that interval. That's always going to be true. Yeah, but now we have to actually check. Does it actually work for the 3 and the 5? Right, this might be a question. So here you want to test the endpoints. So if I plug in x equals 3, go to the original series, plug in x equals 3, notice that I would have the series n goes from 1 to infinity of minus 1 to the n over 2n. Does that converge? It does converge conditionally, yes. So this you'll notice it's 1/2 times the series of minus 1 to the n. This guy was the alternating harmonic. We actually showed it converges, so you can just write converges by alternating series test. And then, if you go to x equals 5, if you plug that in, plug in 5 here, you'd actually get 1 to the n, which is just 1. So this is 1 over 2n. Well, that's just a half times the series of 1 over n. But this diverges because it's harmonic. So here's a series who converges at the left endpoint but does not converge at the right endpoint. So this means the interval of convergence is, it includes 3 but not 5. I can plug in any x value between 3 and 5, inclusive of 3 but not inclusive of 5, and this series will actually converge to something that makes sense. It'll converge to a real number. Whereas the radius of convergence is 1. Which I can think of it as, I can think of this as half the length of the interval of convergence. So this series shows up and I say, find the radius and interval of convergence of this series. You immediately jump into the ratio test. You're going to bound that absolute value by 1 to force the ratio test to work. And so what you'll notice is that the series, it'll give you an interval where it works. You check the endpoints individually. To check the endpoints individually, it's literally just you checking whether or not a particular series converges, which our last 3 classes was all about that stuff. So you should be able to look at something and know, oh, that's the absolute alternating series test tells me about this. Or the integral test tells me this. Or I can compare this with the P series and figure that, right? You're going to use one of the previous series tests to determine does it converge at the endpoints. Then you'd be able to write down the interval where it converges, whether or not it includes the endpoints. And the radius of convergence is just going to be half the length of that interval. Hello? Questions? All right. Let's go with the third example. The third one is another interesting case. We're just a few minutes left anyway. So example C, we had the series n goes from 0 to infinity of x to the n over n factorial. Now of course if we were to write that guy out, that would look like 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus da da da, going on forever. Alright, that's like 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus x to the 5th over 120 plus da da da. Right? So it's just an infinite polynomial that follows that pattern. Now you might ask, what x values am I allowed to plug into this thing, and is it going to make sense if I do that? So how do we figure that out? Well, the same way we always do. We ratio test. So we're going to set L equals the limit in absolute values, x to the n plus 1 over n plus 1 factorial times the reciprocal of this. Now, we've seen things like this before. This guy cancels that. The n factorial is going to cancel the factorial part of that. and I'm going to have x over n plus 1. So what's that limit? Zero. So where does this converge? Nowhere. It's actually the opposite. Everywhere, actually. Yeah, 0 is actually always less than 1. Notice I'm in a situation where it does not matter what x value I pick. I'm going to get that limit to be less than 1. Because 0 is less than 1. So it's actually always less than 1. This is actually a very easy case here. Your radius of convergence is infinity. Your interval of convergence is the entire real line. This guy converges everywhere. Yeah, so 0 is less than 1 always, which means regardless of what x is, I am going to get a limit less than 1, meaning I'm allowed to plug in anything for x, it's not going to matter. There are going to be times where you might get a number here that's always bigger than 1, and at that point you can say, well, it's only going to converge if I plug in the center point and I just eliminate the whole series as a whole, and it won't converge anywhere else. But this is an example of a series that converges for all x. I can literally plug in any x value I want here, right? 356 to the n over n factorial. Eventually it's going to converge. It's going to actually add up to a real number. This will add up to a real number no matter what x value I plug in. Now this is actually a special series, and some of you might actually know what this is the series of. We'll actually get to this guy, I believe, in the next lecture. But in terms of what we wanted to do today, this is pretty much it. I just want to follow up for a follow-up question for the next lecture. So here's something I want you guys to think about and answer by the next lecture, which is on Wednesday. Question. The first guy that we looked at. What does this series that first guy, we know it converges. We know that it converges on the interval -1 to 1, not including the endpoints. What does it actually converge to? That's the question that we're going to answer at the beginning. Does anyone know right now? Does anyone know off the top of their head what this would converge to? This is the guy 1 plus x squared plus x cubed plus, should have a kind of pattern that you can pick up on. Well, think about it for next time. Think about it. That's what we're going to start with the discussion next time. So we're going to actually figure out what this guy adds up to, and we're actually going to use that fact to actually figure out a lot of other cool things and kind of segue nicely into something that we call Taylor series. It's going to be really, really cool. At least I think so. So think of this. What does this series converge to? We know it converges as long as I plug in an x value between -1 and 1. If I do so, what is it actually going to converge to, is the question. And we'll stop there. So. Well then go back, watch the lecture very slowly, and if you have questions, come with them next time. So for now, we want to wrap up. So yeah, know about the series approximation. First of all, we've done a lot with series. Know how to tell when a series converges. You should also know how to estimate how close you are to the answer for a series if you add up the first few terms, the first n terms. You should know this specifically for the alternating series test, for the integral test, and for the comparison theorem with p-series. Then you should know what a power series is and how to find its radius of convergence and interval of convergence. So how do you do that? You always use the ratio test. That's going to give you the interval of convergence right away. You check the endpoints individually using series tests, and then half the length of the interval of convergence is the radius of convergence. Then come up with this for next time, and we'll move on there. Also, as I mentioned, quizzes and tests are suspended. I will be giving you mock quizzes and mock tests, which I'll be posted on the class website. Whenever I do that, I will let you guys know. Whenever I figure out how I'm going to administer tests, that it has to be something sanctioned by the math department. As soon as they come up with a good answer and they distribute that information to all the instructors, I will let you guys know, okay, here's how we're going to do the test, and at that point I'll give you guys it'll be like a week before I actually administer the test. Yeah, don't worry about your grades so far. Like I said, I still count improvement a lot, and I'm going to make it as fair as possible, right? So it's a tough time for everybody, and of course I don't think you guys or anyone should be punished for this. So as long as you put in the work, you will be fine. Other than that, any questions before we leave? Like general questions. If you have any math questions about anything I did today, I would recommend that you go back, watch the lecture after I post it on YouTube, this version, and you can start at the start of next lecture. I might even take some more questions on this before we actually get into this. But just anything a little bit more general, concerns, anxieties. Are you on sync with the other classes? No, the GH class is actually behind. You might remember. This was true because there was a time where we had some sort of holiday and we didn't show up. So there were 2 weeks where we had one class in that week where the RS section did not, right? So there are a couple of days during the semester where we're supposed to have a Monday schedule on a Tuesday or something like that. So this is before this whole pandemic thing happened. We were like a lecture or two behind normally. So yeah, we are behind, but there are days that are coming up in April where we're going to catch up. So ultimately we're going to catch up at some point in April, but currently the GH section is actually, I think, 2 lectures behind the RS2 section. Oh, there is no attendance policy now. So attendance, pretty much how your attendance have been like the month before this, I'm just gonna keep that. And like your attendance grade, I'm gonna freeze it. So I think a month of attendance is pretty good test as to your habits of showing up. Other than that, I don't think, if I were to actually keep attendance now, one, it's not really going to be fair. There might be some people who actually legitimately can't log into Zoom whenever class is in session for whatever reason. I don't know what situation you guys are in out there. And 2, I don't actually think if you get a perfect attendance record from now to the end of class, it's not actually going to change your grade that much, actually. Right? So attendance in general is like 5% of your grade, and there are going to be, so it's not really gonna change your grade much. So if I just freeze attendance as is now, I don't think much is gonna happen. The other camera is running out of battery. I think it's gonna close down soon, but we're done. Okay. All right, everyone take care, be safe. That's it for today's lecture. Think of that question for next lecture on Wednesday. Same place, same bad channel. and be safe out there. Keep working hard. Do your homework. Be safe, and I'll see you guys in the next one. So have a good weekend. Have a good night. Goodbye, everyone. That's it.